right, as we get started, classwork's on the board. 3 problems for you to work there at your seats. Light travels from quartz into air. It's incident at 27 degrees. I want you to find the angle of refraction. You'll need to use that table of refractive indices on page, I think it's 294. Then light traveling through air into a liquid is incident at 41 degrees, refracts at 29.4 degrees. Find the liquid's refractive index. And then finally, something that we did in class with light traveling from water into air. If you want to find what that critical angle was from water into air. Just a few moments to work on these, and then we'll get into picking up where we left off yesterday. Michael, we do hope you get feeling better soon. Audrey's got him. Michael will be like, yeah, I'm done too. He paused the video though, that was cheating. And Kendall's finished. If you're not finished, go ahead and pause the video. If you didn't already do it, Michael. And let's go ahead and take a look at this. 3 equations that we need to know so far. One of them is for the refractive index of a medium. You did not need this equation for any of these problems. The first and second problems needed you to use Snell's law, that first law of refraction. And what is that, Kendall?
N sub 1 sine of theta sub I equals N sub 2 sine theta sub R.
There we go. And so in the first problem, quartz will be the first medium. What was the refractive index for quartz, ladies?
1.46.
1.46, I believe is what we should have plugged in there. And we'll take the sine of this incident angle, which was 27 degrees. Divide out the refractive index of air, which I remember that one, 1.0003. Not sure why my one curved like that. And that'll be times the sine of the refracted angle. So we need to take the 1.46 times the sine of 27, divide out the 1.0003, and take the arc sine at the end. What do we get for the refracted angle from quartz into air in this particular case, Kendall?
42 degrees.
Rounded to 2 sig figs, we'll say 42 degrees. Audrey, did you have that? Excellent. For the second problem, the light's starting in the air, so n sub 1 would be the 1.0003, and we know the incident angle is 41 degrees. Then the light is refracted at an angle of 29.4 degrees. The question is, what is the refractive index of this particular liquid? What is the n sub 2? So here we'd have to multiply these 2 values and divide out the sine of 29.4. And what do we get for the refractive index here, Audrey?
1.34.
1.34, only slightly more optically dense than what we would normally say water would be. It might be water with an additive. Maybe, for instance, you add pine salt to the water, and so it increases the refractive index ever so slightly. I don't know that it would necessarily, but something very similar to water there. We both good on the second problem. Then for the third problem, we need to find the critical angle, and so Audrey, that brings us to our third equation so far that we have in chapter 20. And what is that equation for critical angle?
I know it's n2 over n1.
It is something about n sub 2 over n sub 1. We're finding the critical angle. So sine of theta sub c equals n2 over n1. So the second medium in this instance class is air, so that means we're going to start with a refractive index of 1.0003. We're going to divide that by the first medium, which was water. That's 1.33, we may remember. We'll divide and take the arc sine. And what is that critical angle, that incident angle that would produce or initiate total internal reflection? Kendall?
48.77.
Good, we'll round it 48.8 degrees. Do we get 48.8 degrees? Any questions on this math? I feel like we've worked pretty well on this. Should be good to go there. That leads us into what we started looking at yesterday. We began talking about lenses, and we said that a lens is simply some transparent object whose surfaces are not parallel. Good. So long as the two surfaces are not parallel to each other, it's going to distort the light or bend the light in some way and thus cause refraction. We said really two types of lenses, not two shapes of lenses. One could argue 6 basic shapes, and then of course you can take all different variations on those shapes. The 6 basic shapes of lenses, the 2 categories of lenses. What are the 2 categories of lenses, Audrey? Converging and diverging lenses. And we said a converging lens causes light rays to do what? Come together. And we looked at the 3 different sizes of converging lenses yesterday, and they all cause the light to converge at different points, but they cause light rays to come together. And then the other type of lens was the diverging lens. What does a diverging lens do?
Scatters light.
That's one way to put it, I guess.
Go opposite directions.
Causes them to spread out. There you go, cause them to spread out. I think of maybe, for instance, that whenever I hear diverge, I always think of that Robert Frost poem that no one knows the whole thing, they just know the first line. 2 roads diverged in a yellow wood, and I took the road less traveled. Anyway, diverged, right? There's these 2 roads, and they go in opposite directions. They spread out away from each other, right? And if you pick one, you are, by default, not picking the other. You're going to end up at a very different place because the roads diverge. They go away from each other. They spread outward. We looked at a couple of lenses, my glasses for one, and then of course we had the other diverging lens that we used yesterday. By the way, after I recorded the video, I found a video that kind of shows what we did in class. So I did put that in the description of the previous lesson. So if you're watching on YouTube and you're like, I couldn't see anything in that video, in the previous video there is a link in the description that gives you a little bit better view of what we were doing. It's not as cool as what we did, but anyway. We began looking at lenses, and we said that a lens has one particular point in the very middle of the lens that we'll refer to as the optical center. Through the optical center, then, we have the place at which we will assume refraction takes place. It doesn't actually happen here, it happens at each surface, but we said we're going to assume the refraction, for sake of ray diagrams, for instance, happens at a place called the optical plane. So although there is a true optical center, and again for eyeglasses, the goal is to get the optical center lined up with the pupils. That's primarily where we're seeing. So of course, by the way, glasses usually do not extend as high above the eye as they do below the eye, right? So it's not actually the center of the lens, it's the optical center of the lens. But the optical plane is where we'll assume the refraction takes place for the purposes of ray diagrams. Running perpendicular to the optical plane through the optical center, we have an imaginary line, so to speak, that we call the principal axis, right? Same as we had for a mirror. And for the principal axis, we said that as light passes through the lens, the light rays are going to converge at a point called the focal point. The difference is on a mirror, they strike the mirror and reflect to a focal point. For a lens, they go through the lens and converge at a focal point. At least for a converging lens, that is the case. So we said the focal point is going to be beyond the lens, at least for a converging lens. We'll assume it's out there. Now, is that focal length half the radius of curvature? Just like for a mirror. No, there's actually three things that affect that focal length. Do you remember what they are? There's two different surfaces that curve differently. So they actually have two different radii of curvature. We're going to look at that a little later on in the lesson, Lord willing, if we have time. And then also the refractive index. Because again, mirrors, it just reflects the light. Lenses, depending on the transparent substance the lens is made of, it'll refract the light, bend the light either more quickly or less quickly. So all three of those things play into the focal length. Wherever that focal point is, there's another key point beyond that called the double focal length. The 2F is how we'll represent it. Then on the same side of the lens as wherever the object is placed, we have that same focal length backward. We called that point the secondary focus. We labeled it F prime, and then we had a double secondary focal length as well. And those were things that we wanted to use in our ray diagrams. So we might have, for instance, here's our optical plane, here's the optical center. Maybe we have a surface that bulges here. Maybe we have a surface that has a more pronounced bulge here. I don't know, they don't have to curve the same way. Our lenses in class did, that just made life a little easier, but they don't have to necessarily. And so we said that for this particular lens, maybe the focal length is here. Well, that means that the secondary focal point would be here. If this is the focal point, there's your double focal length. And then, of course, you have your double secondary focal length as well there. For our objects, we said if we were to put an object, maybe it's a Christmas tree, okay? And no presents. And we have a little Christmas tree, and that's the object. It's a small Christmas tree, bonsai, in front of a very large lens, okay? And we put this object in front of the lens. We said to draw a ray diagram, we have three principal rays. They happen to have the same names as the three principal rays before. We just think of them maybe slightly differently because, again, light is passing through the lens ideally. Kind of one of those principal rays was the central ray. And the central ray, and we're going to freehand these for sake of time. Of course, if we wanted to draw them really well, we'd use a straight edge and all of that. But the central ray passes through.
Center.
For a mirror, it passes through the center of curvature. For a lens, it passes through a different center. The optical center. And so it'll come to the optical center. Because it's hitting the optical center, there is no bending, there is no deviation of this ray. It'll continue right on its merry way. So there we have our central ray. Let's see, we had, come this way here a little bit, there we go. Another ray, Audrey.
Focal ray.
The focal ray. And I'm trying to remember which color the book uses. I think it was the pink. The focal ray goes through?
Secondary focus.
Good, not through the focal point, but through the secondary focus. And when it hits the optical plane, now again, this ray actually won't even hit the lens the way I've got my lens drawn, but in theory, there's an infinite number of rays. So one of these rays, anyway, it'll hit the optical plane and we'll have it refract parallel to the principal axis. So something like that is what we'd be seeing. And then finally, the last ray, Kendall?
Parallel.
The parallel ray, and that one starts out
Parallel.
parallel to the principal axis till it hits the focal plane. Again, technically it refracts twice, but for our purposes, hits the focal plane. It'll then refract remember, in theory, all parallel rays should refract through what point? The focal point, right? We're only going to draw one parallel ray, so we only have this one ray go through the focal point. But in theory, it'll go through the focal point. And I'm not sure how accurate that is or isn't, but hey, it looks good. It kind of converges at the same point. The lines may have curved a little bit to make it happen, but hey, that's, you know. And so we get the idea that our image would end up forming somewhere out here. Now notice if we compare this original object with this image, we notice the image appears to be larger. We also notice the image appears to be inverted. And finally, because the image actually goes through the lens, which is what light should do, it appears to be real. Remember, for a mirror, light should reflect off. So if it does, it's real. If it seems to be behind the mirror, that's virtual. Well, for a lens, the light should go through and form over here. So that would be real. If the light seems to stay on the same side, that's the virtual image. That leads us then to what we started looking at the very end of the hour yesterday, and those were our cases of image formation. Cases of image formation for a converging lens. Again, the book uses the double convex lens for all of the converging lenses here, but we see the different sketches. By the way, what you see there at the bottom of the page, their case 3 would be my case 4. Theirs also missed the lens, just pointing that out with the focal ray. Anyway, so case number 1 we said is not actually in your book, but we said for an object, a light source, an infinite distance away, class, the light rays should infinite distance away. So we're thinking like sun, moon, or really bright light way down the street. Okay? Hits the lens, what should happen? It should form a point image where? At the focal point. And the infinite distance doesn't even necessarily matter too much there, because we even saw with some lasers yesterday, we weren't an infinite distance away, and yet the lens handled it fairly well. Now, if you take an actual object, and we're going to do this here in a little bit, now this really won't show up well on video, we're not even going to try. So if you're watching on YouTube, I've got a separate video for you to watch a little bit later. We're going to do some interesting stuff with it, though, here in the classroom. But if the object moves closer, an actual object, now it would have to be an illuminated object because light has to go through the lens, but an illuminated object placed closer but still beyond double the focal length away. Again, that depends on the lens. If it's beyond the double focal length away, we said that the image formed, as we see in the ray diagram there, will be real. It'll be smaller, as we noticed, their case 1, my case 2. It'll be reduced, and of course it'll be inverted. So a real, inverted, reduced image is formed if the object is greater than double the focal length away. That's very similar, of course, to the object placed beyond the center of curvature for a concave mirror. That was also real, inverted, reduced. But it reflected real, inverted, reduced. This one goes through the lens, real, inverted, reduced. Remember, as we brought the object closer to a mirror, when it got to the center of curvature, which was double the focal length, the radius of curvature away, the image would form directly below it, real, inverted, unmagnified. Well, here it's not going to reflect off, it's going to go through, but you notice their case 2, my case 3. If the object is double the focal length away, case 3, if the object is double the focal length away, if the object is double the focal length away, you'll get a real, inverted, unmagnified image. Real, inverted, unmagnified image. Real, inverted, unmagnified image. Remember with the mirror, if you brought the object closer, so it was between the center of curvature and the focal length, the focal point, then you would end up getting this real, inverted, enlarged. Well, the same thing happens with the lens. As the object gets closer, between double the focal length and the focal length away, between 2f and f, or 2f prime and f prime, gets here, then we see what we just saw on the board. This is case 4. If the object is between the focal length and double focal length, you get real, inverted, enlarged images. Real, inverted, enlarged images. If the object is between the focal length and double the focal length away, you get real, inverted, enlarged images. Now track what's happening here. If the object is an infinite distance away and all those light rays come in, they all converge at the focal point, little bitty, just a spot of light. As the object moves closer, the image might form out here. So it's reduced, real, and inverted. as the object reaches the double focal length, the image forms actually at the double focal length on the other side, real, inverted, and magnified. The object continues to push closer. The image continues to not only get bigger, it's also moving further away, isn't it? So as this object moves closer, the image would get bigger and move further, moves closer, bigger, and further. Till if you put the object at the focal point, the image is now going to be infinitely large and infinitely far away. Kind of like if it went at the focal point for a concave mirror, you got no image formed. So that's your case 5. If the image is placed the focal length away, if the object is placed the focal length away, no image. The object is placed the focal length away, no image. The last case would involve the object being placed closer than the focal length away. What's going to happen now, as you see in your textbook, the light rays that go through the lens will never converge. However, it will seem as though they could converge back here, to where the image seems to be formed back here on the same side of the lens. But light rays don't really do that. I mean, technically some light, yes, does reflect off of the lens, but they certainly don't refract through the lens. So you'll produce a virtual upright enlarged image, as you see there in their case 5, my case 6. So case 6, if the object is in front of the focal length, if the object is in front of the focal length, or closer than the focal length, you could say, you get a virtual upright enlarged image. Do you see how every one of these mimics the concave mirror? So if you've got those memorized, take the analogy over here to the lenses. You should also write this down that case 6 is how a magnifying glass works. Case 6 is a magnifying glass. You hold that bulgy lens, right? You hold it over something. It doesn't appear that the image leaps through the page. The page still seems to be down behind the lens, doesn't it? It just appears bigger now. And that's that virtual upright. It's not flipped upside down. That can make it hard to read. Virtual upright enlarged image. So a magnifying glass would be an example of case 5. Some types of reading glasses kind of do the same thing where they'll magnify the image. Now, diverging lenses can only really do one thing. And they're what we saw yesterday when I held up the diverging lens for you all to see. Diverging lenses can only ever produce, well, because light rays never really converge, do they? If the light rays always spread outward for a diverging lens, then the image would always have to seem to be formed on the same side. I take my glasses out here. Kendall doesn't seem to be over here with me. Kendall still looks like she's over there. She's just really small now, right? And we did that yesterday with the other diverging lens. Diverging lenses always produce virtual upright reduced images, which is the same thing a convex mirror did. So the diverging lens, very similar in its behavior, at least in the case that's formed, I guess we should say, to that of a convex mirror. So again, it should make it pretty easy to remember these cases if we remember the mirror cases. Diverging lenses always form virtual upright reduced images. Virtual upright reduced images. All right, I was hoping we could do some lab work and then come back. I don't think we're going to have time to come back to another video. So we're going to end the video here. There is no homework this evening. If you would, though, watch the video link that's in the description if you're watching on YouTube. And ladies, we're going to go ahead and play around with some lenses.